Hey everybody, it's time to learn a new type of substitution different from U substitution. It's called trigonometric substitution, and that's what we're going to learn about in this section. Now, this is used in some really specific situations. We're going to look at three, but you can make some changes to the integral and still get this method to work. Usually, though, we are looking at either one of these three options here. So the square root of a constant, a squared, minus x squared, or the square root of x squared plus a squared, where they're both positive, or the third option where the constant is the negative. So each one of these has a little bit different substitution, but they all follow the same kind of pattern and rules when it comes to doing a trig substitution here. With this first one, if the constant is positive and the x is the negative, then I'm going to choose x to be equal to a times the sine of theta. Okay, this is a substitution just like a u substitution where all the x's are going to get swapped out for some new variable. We usually use theta or t for this. So I swap out the x's for a sine theta and then take the derivative of that to figure out what the dx will be replaced with. So don't forget this step. It's easy to skip over that and just switch dx and d theta in the integral, but it's never dx equals d theta with these trig substitutions. So dx here is going to be a cosine theta d theta because the derivative of a sine theta is a cosine theta. Something else that's going to help us out in solving this problem is this triangle over here on the right. We're using the triangle definition of our trig function sine of theta to fill out the sides of the triangle. So if I divided the a right here over, and I have x over a equals sine theta, then that is opposite over hypotenuse. That is the triangle definition of sine theta. So the opposite side is x, the hypotenuse is a, and the third side, which can be found using the Pythagorean theorem, should be equal to the square root we have over here. And this is why everything works out, is because of this relationship with this particular trig function. If both a squared and x squared are positive, then the substitution I will use is x equals a tangent theta, and the derivative of that will give me dx, which is a secant squared theta d theta. And then here's my corresponding triangle using the triangle definition of tangent, which is opposite over adjacent. And the third type of trig substitution we'll see is when the constant a squared is negative, and in that case, x is going to equal a secant theta, and then dx will be its derivative, a secant theta tangent theta d theta. And then here is that corresponding triangle using the triangle definition of secant. Through the homework and additional guided practice, you're going to get to see examples of all of these. We're just going to do one of them today. So here we have 2x dx over the square root of x squared minus 16. This square root at the bottom here is what tips me off. It makes me start thinking about trig substitution. And because this is an example where the 16, the constant, is negative, I'm going to choose that last option for my substitution. So x will equal 4 secant theta, and that 4 came from the square root of 16. And so the derivative of that will be 4 secant theta tangent theta d theta. And now I know, okay, this is what dx will be replaced with. I know what the x in the numerator will be replaced with. Now the longer version of solving these problems is to also just replace the x in the x squared here with 4 secant theta and then simplify that out. I am going to show you a shortcut. And really we like this because these problems can get rather long. And so anywhere where we can, find or simplify things a little more quickly is a nice thing. So the trick is to pull out that triangle. So here's the triangle for secant equal to 4 over x. And what the trick is, or our shortcut, is you always just take this triangle and look at the constant and the root sides. And I take the root over the constant. Okay, so my root here over 4, and look at what sides of the triangle that is. So here it's the opposite over the adjacent, which is tangent. So I know that the root over 4 will equal tangent theta. And if I multiply that 4 over, I now know that this root is going to simplify to 4 tangent theta. And I didn't have to go through all the work of plugging in the 4 secant theta here for x and simplifying this all out and using trig identities and so forth. It's a nice quick way to figure out what the root will simplify to. So now I have all the pieces of the puzzle to do my substitution. I know what x gets replaced with, what dx gets replaced with, and what the root gets replaced with. So if I come over here, I brought the 2 out front, and then x was replaced with 4 secant theta, dx is replaced here, and the root is replaced at the bottom. At this point, if you've done your substitution correctly, you should always get some kind of simplification going on here. And I can see that the tangents are going to simplify nicely, and I can rewrite these secants as secant squared. I also have some constants floating around that I can clean up. So all the constants should end up simplifying to 8, and then I just have secant squared d theta left in the integral. And I did pick an easy one for this introduction to the topic. Luckily, I know the antiderivative of secant squared is tangent, so I can integrate that pretty quickly. And this is 8 tangent theta plus c. Now, just like with any substitution, I need to always get back to the original variable. So I have to reverse my substitution here. And this is where the triangle comes back into play. I just have to know, well, what is tangent theta equal to? And so I can go back to my triangle, and I can see, well, tangent is opposite over adjacent, so that's going to be the root over 4. And so I can replace that here and simplify. So the 8 and the 4 simplify to 2, and then I just have the root plus c. And that is my answer, and that is how you do a trig substitution. Now, they can get a lot longer than this, so I highly recommend using this shortcut. And here's one more example to try on your own.